Earlier in the term, we talked about how to find sine of alpha plus beta. But how do we know? We will begin by taking a trip back to geometry. Here I have constructed two angles. One we will call alpha, and one we will refer to as beta. Now, because I know what the formula is, I'm going to evaluate sine and cosine of both alpha and beta because it may come in handy later. Now again, all of this is in general form, so we're using letters, we're not using specific values. Begin by drawing a line from point D that is perpendicular to line AC. We want to create the right triangle for which the focus angle is beta. This is perpendicular to AC, and it's perpendicular at the point, let's label this F. Focusing on beta, let's label the sides. This is my opposite side. This is my hypotenuse, and this is the adjacent side. You can also label the opposite side with letters, D, F. The hypotenuse would be AD, and the adjacent side is AF. Sine is equal to the opposite side over the hypotenuse. So sine of beta is equal to DF over AD. And cosine of beta, which is the adjacent side over the hypotenuse, is AF over AD. Draw a line from point F that is perpendicular to the line AB. We're going to label the point at which it intersects AB as G. Now our focus angle is alpha, so label the sides according to this angle. The opposite side is here. The hypotenuse is AF, and your adjacent side is AG. AG, FG, and AF. Let's complete those ratios. Sine of alpha is the opposite over the adjacent, so FG over AF. And cosine of alpha is the adjacent side over the hypotenuse, so AG over AF. And because we began with sine of the quantity alpha plus beta, we need to come up with labels for what ratio that is, okay, labeling it with these points. Alpha plus beta, we have not created a triangle, a right triangle, for which alpha plus beta is the focus angle. Go ahead and draw a line from D that is perpendicular to AG. We're going to call this point of intersection, connection, E. If alpha plus beta is the focus angle, then our opposite side would be this green thing, and that is DE. And the hypotenuse would still be AD. Your adjacent side is AE, but right now we're focusing on sine, so we're not going to talk about the adjacent side. So sine of alpha plus beta is DE the opposite side over AD, the adjacent side. Now, if any of these other acute angles here, 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 if any of them are also equal to alpha or beta by some geometric properties, that could help us to find alternate ratios to represent sine of alpha or sine of beta. To save you some time, I'm going to show you which angle is going to be most helpful for us to try to estimate. Recall as well from geometry that complementary angles are two angles for which the sum is 90 degrees. And the two acute angles in a right triangle are complementary. So I'm going to label this as a different angle, so theta. Alpha, theta, and this right angle make up the angles in this triangle. Now all the angles add up to 180 in a triangle, triangle angle sum theorem, meaning these acute angles are going to add up to 90 because 90 plus 90 is 180. Let's make a note of that. Alpha plus theta is 90 degrees. Vertical angles. So if this angle is theta, this is also theta. Okay, so the angle that we're trying to find is this one right here. Let's call it x. Theta and x and 90 make up the angles in this triangle. So theta and x are complementary angles. Theta plus x is also 90. If alpha plus theta is 90 and theta plus x is 90, then alpha plus theta is the same as alpha plus x. If you subtract theta, then you get that alpha is equal to x, which was pretty intuitive, right? Alpha is equal to x. Ooh, so we found an angle that is equal to alpha that could potentially help us later. For the purpose of ratios that will help us later, we're going to draw a line that extends from the point F and is perpendicular to the line DE. That will intersect at the point H. Now, if this is also equal to alpha, that means we have some additional values or other representations for sine of alpha and for cosine of alpha. Let's label the sides. Opposite angle alpha, this angle alpha, is this side. The opposite side is HF. The adjacent side is DH. And the hypotenuse can be labeled as DF. So an additional ratio for sine alpha would be HF over DF. And an additional ratio for cosine alpha would be the adjacent over the hypotenuse, so DH over DF. To create a formula that related all of these segments, the mathematicians came up with an equation that they knew was true. The length of segment DE is equal to DH plus HE, segment addition postulate. But HE has very little significance because it is not the opposite side of any triangle, the one with alpha or the one with beta. But we do have something that's equivalent to HE. HE is the same length as FG. So we can replace it. HE is congruent to FG. Therefore, we can rewrite this equation as DE equals DH plus FG. We don't want to know what DE is necessarily. We want to know what DE over AD is. So we're going to divide both sides of this equation by AD to create equivalent expressions. Something equivalent to DE over AD, which is sine alpha plus beta. This simply becomes DH over AD plus FG over AD. Now this is when the ratios from earlier really come in handy. We want to know, is there any way we can make these ratios resemble these? DH over AD. Do we have any DHs over AD? No, we have a DH over DF. Interesting. Okay. Do we have anything with AD on the bottom? Anything over AD? This one right here is over AD, and its numerator is also DF. Oh, so what we can do is multiply this ratio by a special form of the number 1 called DF over DF. The goal is to get ratios that I actually know the value of, or can label in terms of sine and cosine. Now we'll take a look at the next ratio. FG is in the numerator. Are there any ratios that have FG in the numerator? I see sine alpha. And its denominator is AF. Is there any place that has AD in the denominator? We have sine beta, and we have cosine beta. But only cosine beta has AF in the numerator, and sine alpha has AF in the denominator. And that's what we need to match up so that we can multiply by a special form of the number 1. And in this case, that form is called AF over AF. When we multiply fractions, we multiply numerator times numerator and denominator times denominator. And because multiplication is commutative, 2 times 3 is equal to 3 times 2, it doesn't matter the order, we can rearrange the order so that these ratios look a lot more like the ones to the left. So we'll write DH with the denominator of DF times DF over AD. Same expression, same meaning. And here we'll write FG over this denominator, AF, and AF over the denominator, AD. Let's substitute the equivalencies to these ratios. So DE over AD is equal to sine alpha plus beta. DH over DF is cosine alpha times DF over AD. That's sine beta. Add it to FG over AF is sine alpha. AF over AD is cosine beta. To make it easier to remember, I like to write it with sine alpha as the very first part of the first term, to remember to start with this trig function and this angle. Okay, so if we write them all in that same form, then we'll remember each time. It might spur our memory on what is the formula, what is the identity. Plus cosine alpha times sine beta. That's why sine of the quantity alpha plus beta is equal to sine alpha times cosine beta plus cosine alpha times sine beta. Remember Sinbad and cosine and that whole story? Yep, that's what this is. And you can see that geometry proves that this is a true statement, a true identity. So here are my formulas, the sum and difference identities for sine and cosine. There are also some for tangent, but we're not focusing on tangent for this video. It's also important to remember that sine of a negative input is equal to negative sine of that input, and that cosine of a negative input is equal to cosine of just that input being positive. That's a definition of odd and even functions right there. So we're going to do two examples, just simplifying as much as possible. This is a weird looking expression, but it looks similar to one of the ones above. So let's see which one is it. You have sine, cosine, cosine, sine, and a plus in between. So where do we see that up above? Sine, cosine, cosine, sine, and a plus in between. The formula we just proved. So let's go ahead and decide an alpha and beta. So alpha is what I'll call the first angle. Beta is what I'll call the second. If you decided that 15 degrees was alpha and 30 degrees was beta, you would still get the correct answer. Okay? Sine of alpha plus beta is what this entire expression is equal to. Sine of alpha plus beta. So plug in the values that we found for alpha and beta that we chose. Alpha is the 30-degree angle and beta is the 15-degree angle. Sine of 30 degrees plus 15 degrees, that is sine of 45 degrees. If you look at your trig table or the unit circle, you remember that is root 2 over 2. That's our simplification. Our second and final example starts off with cosine, cosine, and then goes to sine, sine, and then goes to sine, sine. And our sign in between is plus. So we're looking for cosine, cosine, sine, sine, and plus. That is equivalent to cosine alpha minus beta. So we'll label alpha and beta. Cosine alpha minus beta, so alpha is 2x and beta is 5x, and we are subtracting those. You can subtract inside the parentheses cosine of negative 3x. And remember, cosine of negative x is equal to cosine x. So cosine negative 3x is actually equal to cosine 3x, which looks nicer and is more simplified. The thing that is inside of any trig function, sine of whatever, that is called the argument. So when you answer these questions, you want to leave your answers in only positive arguments. So this would be an incomplete answer. Your answer needs to have positive arguments only.